Assembly Language Tutorial Part 6 Section 1. In this section we will talk about conditional processing. Mostly it's related to some of the concepts we discussed previously, like for instance the jump instruction, the loop instruction. So in the loop instruction we primarily saw that we set a value to the ECX register and then it automatically decrements and we run that in an iterative way to do something. But there was another instruction also, jump, which is very powerful and it's going to be very important in forthcoming videos. So in order to dive into that, we first need to understand some of the basic concepts. So primarily the registers, the E flags register or the flags registers, and in that some of the bits, these are the bits: overflow bit, then sign bit, 0 bit, parity and carry. So these are the important bits in the E flags register, and we'll talk about that. So what I'm going to do is I have a demo, and I would show you that for each instruction these bits actually changes. So if we perform certain instruction and some bits have changed in a flag, so based on that we can take some decision. So let's see some of them. So these are the important ones. So we have like demo for all. So I would be putting this in GitHub and you could play around and see for yourself how these things work. So we'll start off with the parity flag. It means is if the number of bits which are being set, if they are even, so parity flag would become 1. So it it gets set, by that it means it becomes 1. It gets cleared, by that it means it gets 0. So we have our breakpoints ready as usual. So let's start debugging. So the instruction is over here, or AL, so that part hasn't been executed, so I'll step through it. I will step into, and these are, by the way, our bits for the eFlags register, and I step into. So you saw that the PE here means the parity flag. So in my slides I have the abbreviation for that as well. So PE means parity. I don't know why it is PE, but that's how it looks in Visual Studio. So it means the number of bits which are being set into the destination are even, and sure enough we have 1010. So 1 bits. So the count of 1 bits is 2, which is even, so that's why the parity flag is set to be 1. Now here we are going to assign 0000. This is B, the number, it ends with B, so it's a binary value, so binary number. So it's going to shove all the 0 bits into the AL register. Let's see what happens. So pay attention to this side always. So now you see that it's red marked, its parity flag is set, and next is our 0 flag. So pay attention to this guy over here, and I'm going to step through it. So as you saw that the ZR, the 0 flag, became 1. So because the destination now it is zeroed out. So that's the point. Like each instruction that is executed here, so the flags get affected. So based on what the values are being set into the flag, so we can take a decision. So next we would move to the sign flag. So here, after zeroing out the AL register, like the low byte of EAX register, like the lowest byte, now I'm going to add this guy over there. So let's see. So you saw that the polarity, the sign flag, it got changed to 1 because now the AL register is 1 byte. It means 8 bits. So if I count the binaries over here, 1, 2, 3, 4, 5, 6, 7, 8, the last bit or the most significant bit, it is 1, and it stands for a negative number. So that's why the sign flag has changed. Now in the next instruction I'm going to clear out EX register, so I exort that, and now the EX register is already 0, and I'm going to subtract a binary number from that, like the bit 1 from that, so it should take a carryover, right? So here we will see that this carry flag would change. So let's see that. Sure enough, we see that the carry flag has changed. Now it could be possible that if we are adding something, so in our case we have taken the example of subtraction, but it is also possible that we want to add something and that it wouldn't fit into the destination, so it would carry over. So that time also the carry flag would be set. Next, again let's clear out EX register. We exort that, clear it out. Now we move AL, all the values. Now what's going to happen is, now the EX register has 7F and all the flags are clear over here. So now in the next instruction we are going to add this guy. So if you see over here, like these two bits, if we are going to AND it, like it's a binary, this is the ANDing operation. So what happens is, in an OR operation, so if you have 1 or 0, either of them, the output becomes 1, right? And in AND, both of them have to be 1. So now what will happen is, 1 ANDed with 1 will yield 0, and the most significant bit will become 1. So it is actually overflowing that, right? So how many bits we have? 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits we have, so it's going to overflow that. So let's add that. So as you can see over here, our overflow bit is set to 1. So all the bits are added. Now this becomes 0 and here 1. So it cannot contain that. So that is why it is overflowing. So that's why the overflow bit is set. So this is like the short demo. In briefly we covered some of the flags. So these will be very useful in the forthcoming videos as well, when we'll talk about jump instruction, because based on the bit values of these flags only, we would jump to a certain label and do something. So now the operation that we talked about here are AND operation. So this is binary ANDing. So 1 0 0 1 and 0 1 1, it becomes this guy over here. Basically, if both the bits are set to 1, then only it remains 1, otherwise 0. Or if either of the bits are 1, so the output will be 1. XOR, what it does is, if two dissimilar bits are there, then the output will be 1. If similar bits are there, it will be 0. NOT is kind of a neg, so it will just flip the bits. Now there are two different instructions over here, test and compare. So what they do is, test is like AND again, but it doesn't change the destination. Basically, if you see over here, we have AND instruction. So if I remove this, if I highlight this guy, so AND instruction and OR. So likewise we could also have test and compare. So even though they also would work like AND, but they wouldn't change the destination field. Like here, when we want to make some changes, the AL, basically the EX register gets changed, so that wouldn't happen in this case. So why it is useful? So we could, even though we cannot change the destination field, but still the flags would change. So without changing the destination field, now you have overridden the value. How do we get it back? So it would be writing more code to get it back. Like you place it in some another variable, then change it, and then check it, and then bring it back. Rather than, what you could do is, by running test instruction, you could just affect the flags, and you would instantly know that what the outcome of this instruction would have been had it been an real AND operation. So it would change, it would work exactly like AND, but it wouldn't affect the register value, it would just set the flags. So based on that, you do not have to modify the value, and you could check the flags and do something on that. Another instruction is compare. So if source and destination are there, you want to know which is bigger and which is smaller, or if they are equal. So likewise, you run that instruction, destination and source. It's again like AND instruction. So you look for zero flag and carry flag. So this is a quite of a handy table over here. If zero flag is 0, carry flag is 1. So I hope it makes sense. So that's why I covered a little demo in the beginning of the video, and if this thing is confusing, probably you should go back and rewind this video, because it's very important. Without flags, all these things will be very hard to understand. So that's why I started the demo in the beginning. So you look for these flags, zero flag and carry flag. If you see it this way, that means the destination is smaller than source, and so on. So I hope you enjoyed this video, guys, and flags are really important, so I wanted to have more emphasis on that, and hope you like this video, and I catch you next time. Bye bye.